This is the first friction problem where we did a moment equation, and I want to do another one. It's kind of like, you have a copy of it. It says here, let's zoom in. It's kind of like, the given is the sketch, and let me just sketch it for you. There's this box up here that has material in it, and the center of that box, the center of gravity of the box is G2, and the weight of that box is W2. Then there's this framework here that's resting on the ground. Do you see the sketch of the ground here? So it means it's touching right here and it's touching right here. And this framework has the center of gravity of G1, and weight 1 is given as 250. It's not in the textbook. I tried to find where this problem was.
You've done this problem.
Yeah,
Yeah,
it was a homework problem.
It was a whole
the guy up there on the top of
Oh,
the
you
thing.
did. Maybe that's why I couldn't find it. But it had to be, well, you didn't do a friction problem though, so it must have been, they must have ignored friction.
Yeah.
Okay, because I was looking through my 3 textbooks I have to find the problem. I couldn't find it in the friction section. So let's do it with friction now. So you're given the sketch. It says find, what does that say?
WB. Find WB.
Oh, right here. Okay, so find WB. So this is what you have to find for static equilibrium, and they want no sliding or tipping. So let's do a table. So I was talking to Jabin a little bit, and the main reason for writing the table up is that you are identifying all the forces and the moments in the system. Many times when students jump ahead from the given and find to start solving equations, you might forget a force. And I want to force you to look at the picture and figure out all the forces, and moments that are given. Okay, Eric, we're up to you. So what are some forces here?
W2,
Okay,
W1,
yeah,
WB.
okay, let's stop there. So W2 and W1, what do we know?
W1 and 2, we know everything.
Right, and actually I need to give you a distance. There's a distance missing here, I'm noticing. So let's give you the heights. So, this value is 8 feet. And this height is 6 feet. And this is 2. And this, okay, let me fix this thing right here. This is 1 foot, this is 6 feet, this is 1 foot.
This is problem 27, chapter
5,
5.
okay, great, thanks. Okay, what about, Eric, what about WB, what do we know?
The direction,
We know the direction, but we don't know the magnitude. Okay, Lucas, what else? What other forces are here? We have W2, we have W1, we have WB. How about connections? What connections do we have here? Right, DNA, not DNA. Oh, yes, but we don't have to break that up. Just let's assume it's all welded together. What about the connections of C and D? What's going on?
I guess they can be fixed.
Just resting on the surface. See here, the surface?
Okay, so they're normal.
They're just normals. So you want to call them normal C and normal D?
Joanne,
Yeah.
I think A and D are kind of, are working.
I made different, since I didn't have the original drawing, I called things differently, so you might not want to look at that picture.
Well, I meant more, did you change a problem? Because A and D are just one component, the D is right up on the
Okay, well, yeah, so I changed it. Just use my picture.
A. Okay.
Okay, so what about the normals, Lucas? Do we know them?
Don't know them, but we know.
so we know the directions. Okay, so we have 2 normals, 3 weights. Did I hear somebody ask something? Well, let's look at what's going on. So let's physically think about this. If there's a weight here and there's a weight here, and it's resting on the surface and there's a weight here, what will happen if W1 and W2 are very large? It's gonna rotate, and where is it gonna rotate about? This point of D, right? Right? If W1 and W2 were so large, it's gonna tip this whole thing down. We saw it, remember the crane? The first couple of weeks of school, we watched the video of the crane that just kind of fell right over. So if W1 and W2 are very large, what's gonna happen to C? It's gonna pop up, right? It's not gonna touch the bottom anymore. We're gonna have rotation on D and the whole thing's gonna fall over. Right? So the normal at C would be 0 if it tips. Okay? So in that case, if we have that going on, which direction is our friction going in? If it has the ability to rotate to the right, the friction's gotta go to the left.
W1 and W2 are
So it's tipping friction against the.
Yeah, because the friction, yeah, it's a friction on the surface, it's 2 surfaces together, right? So we're gonna have, just let me see if I isolated these as 2 different frictions.
Yeah, would it be the right go the other way? It's because it's, the wheel would be turning clockwise, so it should go that way. Because it's being pushed this way.
I didn't even put friction in here. Yeah, I didn't put any friction in the problem at all. Okay? Okay, so how many unknowns do we have? We're up to gradient? 3.
no friction.
Yeah, let's not do friction. Okay? Well, let's just see what happens if we did put it in. Okay? So let's just go up here and do it on the board. How are you guys doing over there seeing this?
I can see it.
Too low.
Yeah? Actually, maybe what we'll do is we'll just, yeah, I'll get it right. Here's the, okay.
Wait, why are we not doing normal at C?
We do have a normal at C.
Okay, I wasn't sure it was.
Oh, that's just a line, I didn't draw a good line.
That's okay.
Oh, no, I'm sorry, it's not a cross out. Rather than redrawing it, I'm just gonna put this on here. So this is my free body diagram. So I have a normal at D. I have a normal at C. I have my weight 2. I have my weight 1. And I have my weight at B. So if we have 3 unknowns, gradient, how many equations do we need? 3 equations. So let's say we put friction in there. What would we find out? If we were analyzing it the way I said, if it's tilting like this and something that's holding it is more rough on the bottom, and we put frictional force like this, how would we determine what our value for the frictional force is? Do an equilibrium equation.
You have to find like countermeasures. You have 2 more unknowns, right? So you'd have to have 2 bodies.
You guys, it's easier than you think, you're making it more complicated. Look at all the forces on there. What equilibrium, yeah, Kyle? Some of the forces in the x equals 0, and what does the friction equal? 0. Then you just determine that friction isn't the problem. Okay, sometimes I think you're thinking it too complicated. Just think of the steps. If you drew the frictional force in there, and put it in the table, and then you went and said, okay, what's the easiest equation to do first? You would have said sum of the forces in the x equals 0, and you would have got the frictional force to be equals 0. And then you just learned that the frictional force is not there.
Is that the case every time you have a tilting?
No, it's not always. It's not always. Because you could have sliding and tipping. You'll find that in some of the homework problems. I picked enough problems that were different and enough problems in class that are different to kind of give you all the different kinds of problems. So Kyle, what equation then? If we did sum of the forces in the y, how many unknowns would we have?
3.
3 unknowns.
Or less, are we not counting normal at C?
Well, no, because right now, if you do the sum of the forces in the y, we would want to keep the normal at C, because we're analyzing it the way it is now, not the pending motion. Okay. So let's just write the equations. So sum of the forces in the y equals, what is it, NB, NA,
NC and D
NC plus ND
minus weight B minus weight 2 and minus weight 1.
Okay, so NC plus ND minus WB is equal to, what's weight 1 and weight 2 equal together? 650. So here's my equation 1. So we're really analyzing it right now just for sliding. And we already learned that the sum of the forces in the x doesn't really help us. So we have to do a sum of the moments about a point. Let's do some of the moments about C, which is on the left. BJ, why don't you walk me through that? Some of the moments about C. So WB times
WB times 1,
1 positive or negative,
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 and then ND times 8, and that's
and D times 8 and
positive.
positive. Let's plug in the numbers. So let's see, W1 is 250. So let's say 250 times,
8.
looks like it's 7.
7.
Positive or negative,
Negative,
negative, and then 400,
400 times 8, and that's also negative.
and is it 8?
It's 9.
I don't think that's 7.
No, it's, yeah, it's 7.
There's a
This
line.
is 1 and this is 6.
Uh-huh.
1 and 6 is 7.
What is 2/3 of 6?
We're not doing it's not a distributed load, it's just a point load.
Oh, okay, okay.
And then this is 1, 6, and 1, and it's 1 up there, so it is 8. Equals 0.
I think it's 2 up there.
It is 2 up there.
Well, it is.
Oh,
Yeah.
It's different than it's cut off. The
Yeah. It is, it's drawn as 2. I'll slide it down. This is off here.
Yeah, that's why you were saying it's not 6.
No, the other one is
This is definitely 7, because this is 6 and this is 1.
The way you drew it there, but on the way, on our sheets, it's not that at all.
1, 6, and 1, that's right, that's what I wanted you to correct it.
It's 8, I have the picture.
You know what, can we just change this 2 up here to a 1, and then it solves our problem?
Yeah.
I like that idea.
Okay, change the 2 up top to 1, and then it basically lines up along here.
Oh, it's actually
But only if you look at that, don't make it because then I have to redo everything up here.
Joanne, if you
Yeah.
wanted to line up, wouldn't that be 0.5?
what?
That's what happens when I'm not drawing it correctly.
No, you're all right.
Yeah.
It's 1 foot to G2
No, no,
and
he's
1
right.
foot
I-
from.
No, Jose's right, it's right here. You guys, let's just do this. 1, let's just make it 8. Okay? All right, so what is this? Negative WB plus 8ND equals, what's 250 times 7? And then 400, so this is 3,200. Say it again?
1750.
Good. So that's 4950. So some of the forces in the X didn't help us. Some of the forces in the Y gave us an equation with 3 unknowns. Some of the moments about C gave us an equation with 2 unknowns.
Moment, either B or D.
Yeah, so now why don't we start, let's see if we could, can't get both of them from that.
Joanne,
Yeah.
if this is being analyzed at the point of tipping,
It isn't so far.
Oh, sliding,
We're just
okay.
looking at sliding, but now we go to the point of tipping. So what is different when I'm analyzing something from sliding to tipping? Well, hang on, Carolyn?
If you're trying to find some of the moments at point C, that 250-pound force does not act at 7.
I'm trying to find the moment of here, C. Here's the weight, here's 6, here's 1, it's 7.
Joanne, look at the sheet that you gave everyone. It's not the same, that's why everyone's freaking
I know, we corrected that.
Okay, but then I changed it.
Yeah.
Yeah, no,
It's now 1 foot from.
Just say it really loud that you changed it, Joanne.
because
I didn't
so the picture's slightly different, so instead of looking at that 2 feet difference, just make that a 1 foot.
Before that. Before that, what I did is I originally had the 6 going from here to here, and then I extended the line of the force and said, no, instead, you see the green here? The green was saying it's 60 here, it's 1 here, and 1 here. So I changed it with the green. Okay. Okay, you guys, in the end, the numbers don't matter. Even in engineering, because you're going to put a factor of safety on it. The analysis is what's more important. So don't get stuck on the little math things. Okay, it's hard for you to get that because you've been doing so much detailed math up till now. But it's the statics that's important. If you put 1 foot in or 2 feet in, it's not a big deal in the scheme of things, right? Right? It's the statics. So when we did sliding, we had all these forces present. And if you had put in the frictional force, you would have found it was equal to 0. Now we're looking at things tipping. And if things tip, where are they going to tip? What's the tipping point? It's at point D. So the tipping is going to be at point D. And when it's going to be about to tip, what's going to change from this free body diagram?
No more.
There's not going to be a normal at C anymore. There's going to be no normal at C anymore because it's not touching. Once it tips up, there's no normal force anymore. So now let's do some equations. Does some of the forces in the X help us? No. So what's some of the forces in the Y now? ND minus WB minus W1 minus W2 equals 0. So ND minus WB is equal to 650. Does everybody agree with that? So I'm going to call that equation 3. And now, where do we want to do some of the moments about? The points that's tipping. So D. Is NC, do I put NC in the equation?
No,
No. If there was a frictional force, would I put the frictional force in the equation when I do some of the moments about D?
no,
Why not?
because it's coming from D.
Because the frictional force goes right through point D. It can't create a moment. Let me say that again. If there was a frictional force in this problem, and I did some of the moments about point D, frictional force goes right through D, so it would have not created a moment. Same thing here. If there was a frictional force, would the frictional force be in this equation? Why not? The frictional force goes right through that point C. That's where it's touching.
Isn't there a little bit of perpendicular distance between point D and the ground?
No, it's supposed to be.
On the flip.
There's a ground, I just didn't. It's touching the ground, right? Otherwise there wouldn't be a normal, it would be floating. It's gotta touch the ground, right? Okay, so moment about D, where are we? Tara Lynn. Some of the moment about D. No, she's just resting. Okay, the distances are gonna be a pain, huh?
Yeah.
Okay, so what forces, let's put the forces in first. What forces are gonna create a moment about D?
WB.
W1, W2, and WB, right? Does ND create a moment about D?
No,
No. Does NC create a moment about D?
no.
Well, it would, but it's not touching, so it's not there anymore. Because it's just about, just impending motion.
I don't see W2 then.
We're back to the distance. Is that what you're gonna say? So it's going through, isn't it?
So we got to set up right now.
Okay.
So it's definitely not gonna tip. There's nothing on the other side.
I'm so glad I had a white towel in my hand. Sarah, we should just put your picture up there and start all over.
You know what, Joanne?
Yeah.
Let's just, all talk and hang out.
Right. And that is static. That you need to have W2 hanging out somewhere to the right of D, otherwise this thing isn't going anywhere. Oh, what a nice picture. We even have a gentleman up there.
All you have to do is keep it
Okay, let's just do this equation based on
Never
that
mess with
picture.
this. This is
Okay, Tara Lynn, W1 is where G1 is. So it's W1 times, what's the distance from G?
From D,
Yeah, it's the point we're finding the moment about.
2 feet.
W1,
G1.
G1, okay. G1 is.
1,
One.
and is it positive or negative?
It's positive.
Positive. W2 times,
No, right.
Charlene,
2,
2, positive or negative?
negative.
Negative. And WB,
Five.
what distance? WB times?
7,
7, positive or negative?
positive.
Positive. Okay, let's go back here then. So WB, we're doing moment about C, so WB is 1, ND is 8. The 250, what's 250, G1?
Yeah.
Yeah.
Yes.
G1 times 7, and 400 times 10. Okay, is everybody all right with the distances now?
Yeah.
Okay, what's W1? What's the value of W1?
250,
Okay, what's the value of W2?
400.
Okay, so 250 minus 800 plus 7 times WB equals 0. What is WB equal to? Come on, pull out the calculator, you got it right there. Wiggle your fingers.
1,050?
Yes.
No?
I thought we were adding.
78.
78.56. Oh, yeah.
78 pounds? Okay, 78.6 pounds. And what do we have to find in this problem? What did they ask us to find?
The smallest counter.
The smallest kind of.
Okay, and that's it, 78.6. So is that a minimum or a maximum?
Minimum.
Okay, well, let's think about it. So if 78.6 pounds are at B, it's not tipping. If we make the weight at B 100, what's gonna happen? No tipping. If we make the weight at B 50, what's gonna happen? It's gonna tip. So is this the minimum or the maximum for static equilibrium? So you guys did this problem, so you did a friction problem already. Without friction. Still. Okay, so you're gonna have, there's a problem, there's a few problems where somebody's pushing a refrigerator or a box or crate or something, and depending on where they push it, it could either tip over, or if they push it low enough, it's gonna be sliding. So you wanna analyze it for both sliding and for tipping. So you're gonna do rotational analysis as well as translational.
Since we're dealing with statics, wouldn't all our values that we find would be minimum?
No, because there are times that we had to find, remember we had a minimum and maximum of the one problem, the block that's on the inclined plane? There was a minimum and maximum because if I pulled it a little bit if I pulled it more, it would have slid up. If I less, it slid down. So there was a min and a max in that problem. So it really depends. Okay? So we did 4 different problems then. We did the sliding problems, we did 2 rotational problems. Is this Sarah's? Okay, so let's take a look at the syllabus on when things are due. So today's Thursday. So our friction homework is due a week from today.